Ladies and gentlemen, welcome to process control. Today we're going to look at how to write a program, a PLC program using TIA version 17. We have done the introduction on TIA, so today we are going to design a program. We are not going to look at this example that we did in class, whereby we have a pool or a dam, and then we have a pump that is pumping water to the tank. So we have three input or our sensors. LLS, it's censoring if the water is below a required level. If it's below, the motor should stop pumping the water. Here we have LLS2. We said this will be 2. Now LLS2 will be looking if the water is below the required level. The pump should be on and pump water. HLS, its purpose is to determine if the required level it's been reached, then the motor should stop pumping water into the tank. So this is what we are going to design today. Now I want just to do this from start, because sometimes you'll encounter many challenges. So I want to show you step by step after you've done your installation. But some other computers may not have this problem. If you open your TIA, normally it will run, but sometimes it will give you challenges. So to be on the safe side, you right click, you run it as an administrator, and you say yes, then it will open. I think this is I will say the safest way of opening it, so that you won't have any challenges. But on a separate video, I will show how to bypass or to navigate those challenges that we have. Now this is our opening page. Now we want to create a new project. We click new project. We write water tank. Let's just say water tank 1. Save time. And then you create a new project. Again, as I've always indicated, you must have a very good laptop. And then, as we explained before, we go to configure, add new devices, then if I'm not mistaken, subjected to be corrected, in our lab we have S7 300, but if not so, we are just doing this in the purpose of just us trying to show you how to do this. Then you can select any for the purpose of us. We will select this one, but let me select this one. This one, I think why I'm selecting this one doesn't have IOS modules on it, so you are required to add it. So the reason why I'm selecting this PLC, it's meant for that. Remember, what we are trying to do now, we are bringing an understanding on how to configure, and number 2, how to write a program. Writing a program will always the same. The only thing that will different, it will depend on the PLC that is in the lab, that you have to check on the PLC that is available in the lab, so that when you configure using that model, you must be able to check from here which model is that. So in this case, we are going to choose this, and then we say add then we'll wait. My computer is a little bit faster, but I don't know what is happening now, or I'm opening so many things, I'm not sure. Okay, we have done the basic things, the introduction to TIA. So if you need to revise it, you can go on the link below and watch the introduction. So I won't go into detail. So now we are looking at, we don't have our what we call your ROs. So here we come here, we have, this is digital input and digital output. We are going to use digital input and digital output only, and then this is the one we're going to use. Click it here, we place it here. So now let me zoom so that you can see we have our PLC and we have our IOs module. So now here you can configure as it is now, but because of time I want us to go straight now how to write a program for this. Now we have put our component that we need, which is our PLC. We also need our IOs module. As you can see here, you can get whatever that you need here. As I said, we have covered that module. We can save this project. If you want to configure now, you can also configure now. You compile, like normally you do this actually when you are really connected to the hardware itself, so there's no error. But let us move. We'll do this after we finish writing our program. Then you go to program blocks. Again, we have talked about this one. Double click here, then we have our network. Let us look here. We have LLS1 to detect the water level of the dam. If it's below required minimum, this must be off. Number 2, we have our LLS2. LLS2 is to detect if the water in the tank is below minimum, below required level, the pump should pump water into the tank. HLS, it's to censor if the water has reached the required level, the high level, the pump must be off. So that is what we are going to do. And again, I want to stress, this is a basic understanding that I want to do. There is a simplest way to do this using your flip-flop, but we will go there. But for now, I just want to do this one so that when you are moving to flip-flops, you will appreciate flip-flops better if we do this one, because the way we are going to do it now, it's a bit longer, but at least you have understanding. And again, there are many ways of doing this. Some people would prefer another method. I will show you as we continue, but for now I will just use this one. Then we here the start button, we address it to 0.0, I 0.0. Then the hour tag, this is start. Then we change the next one. It's a normal close. Normal close, we say I 0.1. This is stop. Change. We have our assignment or output. We call this is our output, Q 0.0. We call this tag on. We want to see if our circuit is on. then we'll put this on, change. Then we want to put our holding circuit, whereby when you remember our start button, you press start and release, the motor or the light should remain on up until you press stop, so that you'll be able to see, like, the motor must keep on rotating, or the motor must keep on pumping water. If there is an emergency, then you press your stop button. So you put this and this, and then we call this Q 0.0. It will pick up this, which will be on. Now this output, it will energize this one. Then when you press start here, we'll have energy going this direction. Then when this one is on, this one will be on. Even if you've released the start button, they will continue to go like this. You will see that when you are simulating. And then this is important, so that you understand what you're doing. So the second network, another disclaimer, I'm making this basic. It's for someone who's doing this for the first time. So I'm trying to bring you into understanding. We'll move in a more complex one, where we're using timers and counters and flip-flops. But for now, I just want to bring this understanding. That's why I'm always trying to emphasize this. So we'll put this one, and this will be a contact also we put here, which will be Q. If you don't understand, now if this one is on, if the circuit is on, then this one should be on. Then here I'm going to put now my 3 sensors: LLS1, LLS2, HLS. These are my 3 input that we are going to use. Now let us look at this one. We are saying here, if the water is below the required level in the dam, the motor should be on. So what I want here, I will make like this. If it's below, it's send 1. If it's below, it's send 1. Here, if it's below, it's send 1, it operate the pump. Here, if it's below, again it's send 1, it stop the pump. So now these two that I want them to stop the pump, I will make them normally close. Make normally close. So this is I 0.2, tag, rename, LS1, change, again this one. Okay, let me maybe just try and do this in order so that I won't confuse you. We've put LS1. We said if it's high, it should stop the motor. So if it's high, it should open and stop the flow of current so that the motor will stop running. Here I will make this a normal LS2. I'll make it open so that when it sends that there's no water, it sent 1, then it will close and the motor will be high. So take normally open, it's I 0.3, tag, it's LS2, change. I hope you are following. Then we look at this one. We say this one I will use a normally closed, so that when the water hits this level, it will open the circuit. So normally closed, we call this I 0.4, tag, rename HLS. Then lastly, we put our motto, which will be Q 0.1, because we have used 0.0 here. And then we call this motto, and then we say change. Now there is a way of checking this all tag. As I've said, some people will do it differently. Go to PLC and then PLC tags. You can click here that says show all the tags, or you can click here, which is like your default tags. You can move here, or here also you can also see this tag. So you can manually do this, assign your address here. As you can see, our start is I 0.0, our on Q 0.0, our centers are on I, our Q, our motto to run it on Q01. And example, we can say, okay, maybe to say motto is not clear, let us change the name to say run. So to determine that the motto will be running, and then this will also change on our OP. You see now it's no longer motto, it is run. So you could do this either way. On the table side, you do that in first, but for me, when you are at this level we are now, an entry level, an introduction level, I think it's better to do step by step, because you just in this, when you are doing this step by step, because you know, okay, this is the first network, the second network, you keep on thinking, then it will populate itself, unless you're now in an advanced level, you know in your mind what you are doing, but sometimes you might need to do this step by step. Okay, now we are done. We save. We are going to try and simulate now this I'm trying, the reason I'm doing this, because the next step that we are going to do will need to have a little bit of space. I've saved, then I compile to check if I do have any error. No error. Then I simulate. Then after you simulate, you'll have this. Let me close this now. You'll have this. Now this is our simulator. In this case now, okay, we are configuring, we are loading our PLC one. We have done it. Sorry. Now we have opened here. As you can see, I've selected stop. Whatever I'm doing, it's like I have not pressed start on a PLC itself, not to run the program on a PLC. So now I'll press this, is to observe, to put classes on it, on this one. Now what we'll see now, as you can see, because it's still like gray because it's on stop, but when you press run, everything will change and show you. Now I think you can see now it's on run. As you can see, the green, it's where it's energized. It stops here. As we can see now, once you press start here, we'll have this. So now, how do you do that? Now remember, it's easier when you have connected this to a PLC, the hardware PLC. But now we are simulating. How do you do that? You go to insert and you input your variables. Now these are your bits. Remember, we have configured, we've addressed our input in this manner. 0.0, this is 0.0, 0.1, 0.2, 0.3. Okay, these are our inputs. So now if I want to press start, I click here. As you can see, I've pressed start. Now it's on. Now if I want to release start button, the circuit should continue on. I release the start button. As you can see, I've released the start button, but now it's energized via this con. So now the motor or the circuit is still on. So if I want to press stop, my address for stop is it's 0.1, which is this one. When I press this one, then everything will start back. It will be reset. So let us now check it now, because what you want to do now, we want to look at this. We make this one high. We see if the motor will run. We stop this one and we make this one high. We'll see if the motor will still run. That's why I'm saying I'm just doing this like in a basic way of trying. The next video that we'll do, we'll try to go into details. For now, it's just for us to have a little bit of understanding. We press start, we release the start button, is still on. Now, as you can see now, it is checking LS1. It's saying LS1, it's fine. It's checking LS2. Now, in this case, LS2 is fine. But if we say this is 3, if you say no, the water is below, we say click here, then you can see the motor is running. The motor is running. It's filling up until it reaches this level. If it reaches this level, let's say this is 4. When you say it's 4, then it will stop. If it's 4, it will stop to fill in the water. Let us make in this case, let's say number 3 LS2, it says high. Then the pump is pumping water. Then there is a problem. You want to stop the whole operation. We have created a stop button. You go to the switch, press stop button, everything is switch off. So here, this is how you do your simulation to observe on this, based on a simulation, not connecting on a PLC hardware. If you're connecting on a PLC hardware, it's different. Again, I know I'm trying just to bring you into the understanding on how this is done. We are going to take it further. We're putting your flip-flops, your counters, your timers, and all those things. But for now, I'm trying to bring a little bit of this understanding. On the next video, we'll do this same problem, but now, or example, now designing it proper, not in this level, because now what I'm trying to do is just to ignite your understanding on how this, and have a bit of a view how this is done. We start, it's on. We release, it's still on. It's checking the water in in a dam, still it's still okay. Then let's make this one high to fill up the tank. You fill up the tank, and then the tank is full. The sensor detects that the tank is full, and then it stop running. Or in this case, let's say LS2 is high. Let's say LS2 is high, but the motor, remember, the motor is pumping, but the system, the LS1 detects that the water in the tank is below the required level, so this one will be on. So you see, it stop everything, the motor stop running, whatever happening, because now this is the one, LS1. If the water is below this level, the motor should stop running, as we can see here. So this is how we write a basic program. These videos, what we are trying to do, we are taking step by step on how we can write this program. Now the next video, we are taking it further to do a higher level of doing this program, so that you'll understand. Then from that, again, we will now try to introduce your timers, your counters, your flip-flop. So thank you for watching. I hope this video did ignite your understanding, as it's designed for that, so that you will have a better understanding.